If this determinant of the coefficient matrix equal to 0, I'm not going to be able to use Cramer method. So I will have to go through the Gauss elimination or Gauss-Jordan that we talked previously. Now it's working, perfect. The second step, to get the values of x1, all I have to do is to just write this determinant once more. But then I will write it on the top of this one. I am getting the values of x1. I'm getting the values of x1, okay? So all I have to do is to replace the first column by 7, 4, and 6. 7, 4, and 6. The remaining two columns will exactly be the same, yes? So they will be -7, 0, 2, and 6, -1, and 5. I will go through how to evaluate the determinants. It's not related to current.
The first step is confusing to me. How did we get that matrix?
This one?
Yes.
Okay, from here. x1, the coefficient is 10. So I should have here x1. So I have to replace these values, which is going to be -3, then 5. This is what you should watch for when you are solving any system of equations. Because simply, you know Gauss-Jordan, you know Gauss elimination, whatever. If I give you that system, you will have to switch first while you are writing the system on the augmented matrix. معايا نور? Okay, more than perfect. So simply, I wrote the coefficient matrix. I will go for the second value. The second value will be x2, which is gonna be simply exactly the same coefficient matrix, which is gonna be on the bottom. So it's gonna be 10, -3, 5, -7, 2, 0, 6, and 5. And for the denominator, I will replace the second column, which is the column of x2 variables. So I will take this matrix, this determinant, and I will put it on the denominator, exactly the same. So it's going to be 10, -3, and 5. The last column will be 0, 6, and 5. I'm just going to replace the second column, which is going to be the 7 and the 4, then the 6. Similar manner to this one, exactly the same. I can now get the value of x3, which will have the same determinant in the denominator. But on the denominator, I will have this coefficient matrix with the first two columns exactly the same like the coefficient, 10, -3, and 5. بعدين 7, 4,
-7 to 1.
-7, 2, and -1. And the third one will be, this is going to be 7, 4, and 6. Then I will get the values directly. So it's very, very simple. But now I will become to the real challenge, is to evaluate the value of each determinant. Knowing how to evaluate it using Sarah's rule, it will make your life easier. Using Sarah's for the first coefficient matrix. Anyone? عبد الرحمن؟ تقدر تقول لي احسبه ازاي؟ 10 times 2 times 5. شايف يا عبد الرحمن؟ بضرب 3 elements دول في بعض. يبقى 10 times 2 times كام؟ times 5. بعدين plus -7 times 6 times -7 times 6 times 5. -7 times 6, okay, times 5. Then plus, vice versa. -1 times -3 times 0. -1 times -3 times 0. In a similar manner, minus, open a bracket. I will go for the other or for the secondary diagonal. معايا بقى؟ Which is gonna be 0 times 2 times 5. Then plus 6 times -1 times 10. بعدين plus -7 times -3 times 5. negative 7 times negative 3 times 5. كده انا evaluated مين؟ نفس الستيب تانية سيف، هعيدها تاني بس فين؟ فوق. same way like هبدا برضه 7 times 2 times 5 بعدين بلس negative 1 times 4 times 8 خلاص مش هكتبه بقى. بعدين 6 times negative 7 times 6. Actually I can solve it using a calculator direct. Okay? If the numbers were similar I can evaluate it by my mind. Okay, تعال بص كده. This is the first value of x1 which is simply the coefficient matrix. Then I will write once more the coefficient matrix on the denominator, replacing the column of the first variable by the results, 7, 4, and 6. Once you evaluate this, it's going to be 0 over negative 155. So the result will be 0 for the first variable. For the second variable, exactly the same. The coefficient matrix already exists in the denominator. Remark, the two columns for x1 and x3 are the same. x2 just only will be replaced by 7, 4, and 6. I will evaluate them, so the result will be negative 1. And this will go for the last variable. معايا ملك? It's really very simple. The only obstacle in dealing with Cramer's method is the size of a denominator. It's the size of a denominator. Just to think about it. If I have a 4 by 4 system, how many determinants I should evaluate using Cramer method? 5 of them. And each one of these 5 determinants, you have no other way. Unless you will have to break it into another 5 4 by 4. So simply, in order to evaluate a 4 by 4 system, I will have, 5 4 by 4. Each one of these 4 by 4, it will be breaking down into 4 3 by 3. So if I'm solving a system 4 by 4, I will have to evaluate 20 determinants 3 by 3. If you try to expand each one 3 by 3 by the cofactor to be 2 by 2, you will end up having 60 2 by 2 determinants. Can you imagine if I have a 5 by 5 system of equations? 5 by 5. How many determinants I should have? 6. Each one of them will be 5 of 5. So it's going to be 6 times 5 times 4, which is going to be 24, 4 by 4, which is going to be multiplied also times 3 to be 4 to be 3 by 3. Okay, you will end up having an unbelievable number of determinants in order to solve a system of 5 by 5. This is why the Cramer method, it's not recommended if you have dimensions bigger than 3 by 3. So it's very, very good method to follow if you have a unique solution. This is number 1. Number 2, for a system of equation within maximum 3 by 3. Other than that, it will be recommended to go through Gauss elimination or Gauss-Jordan method or any other method dealing with a system of equations. This is the major issue about determinants. Because evaluating determinants is not easy, there is some properties that will help you out through the evaluation of these determinants. I will go through them. Some of them, we already know about them and through row operations. Do you still remember the row operations? Switching rows, multiplying row by a number, multiplying row by a number, then adding it on another. Keep those in mind. Okay? Those in mind. Those are the ones of the elementary matrices, and those are the ones of the row operations. Let's see how they are different once you try to go through determinant, the evaluation, or how these row operations will differ once you try to use them with determinants. I will go from scratch once more through all the slides that I sent it to you, step by step. Remark the similarity, remark, now you know how to evaluate them. Okay. Determinants with more details. هبدأ أمشي بقى في السلايدز بتاعتنا بتاعت الرسم. خلي بالك السلايدز دي الابديتد فيرجن 25, it's by Jose. The first of them, he is giving you the axiomatic definition, basic probabilities, and for the Gauss elimination. This is a matrix n by n. The matrix for a square matrix, it consists of number of rows. The number of rows can go up to n rows. Because in the beginning, we know that we can define a matrix by its elements, or can be defined by rows, or defined by columns. Okay, perfect. Next step. To each square matrix, there is assigned special scalar called a determinant, which is a value belongs to the real numbers. Okay, exactly like what we defined. This is the value or the symbol of a determinant. We usually write the matrix, and then we put the absolute parentheses in order to work with it. This is the determinant that we want to evaluate. Also, sometimes we have this notation, det of A, by meaning the determinant of A. We can use either one. Okay, perfect. And then we call determinants to a real valued function, determinant for any matrix n by n, from the real numbers into a real numbers on the space of all n by n square matrices that satisfy the following properties. These are the properties of the matrices. I'm sorry, of the determinants. The first of them, the homogeneity in each row, which means if you want to take a common factor, it's not gonna be coming from all the elements of the determinants. No, it should come out from one row or one column. This is completely different than matrices. In matrices, if I want to take an element as a common from a matrix, I will divide all the elements of the matrix on this value. So, just to make it clear, if I have a matrix, let's say 4, 6, 8, and 10. This is matrix A. This is the A matrix. If you want to take a common from this matrix, you can take this common from all the elements that exist in this matrix. So the result will be 2, 3, 4, and 5. But in case of a determinant, the common will come out of one row of this determinant. So if I have a determinant, let's say 5, let's go for 1, and 2, 4, this is the determinant. Okay, I need to compare it with 5, 1, 1, and 2. And I will take 2 as a common from R2, from the second row. If I want to evaluate the value of this determinant, it's going to be 5 times 4, which is going to be 20. 20 minus 2, so the result will be 18. Let's try once more to evaluate this determinant. 5 times 2 is going to be 10. Minus 1, so it will be 9. Times 2, 2 times 9, so it's going to be 18. So if you try to take a common factor, it should go out from one row or one column. I can do it on rows or on columns, which is completely different than the property of a matrix. Okay? So this is called the homogeneity. The additivity in each row for matrices, and before we start recording, I've told you about that. There is some differences between the properties of a determinant and the properties of a matrix. In matrices, if you are trying to get the addition of two matrices, the only condition is to be of the same dimension. So if I have a matrix 3 by 2, it's going to be added on just only on any matrix 3 by 2. You are adding the corresponding elements in rows and columns. It's very, very simple. But in determinants, remark, if I want to do this, R1 is exactly like R1. Ri and Ri dash, just only the difference in these two columns or in these two rows. Rn, meaning points till Rn, they are exactly the same. Look to the addition. Here is Ri and here is Ri dash. The remaining are exactly the same. With the meaning of, for example, this determinant value will equal to exactly the determinative value of this one. 5, 1, okay, I can put 1 and 3 plus the second determinant to be able to evaluate it. And they have the same results. The change should be in just only one row. So the first row will stay the same. The second row will be 1 and 1. If you evaluate the value of this determinant, we'll find it exactly like the sum of these two determinants. So, which means that If I want to add two determinants on each other, I'm adding just only one row, and the other or the remaining rows should be exactly the same. And also for the columns, it will be exactly the same. شباب انتوا فاهمين معنى كلامي؟ يعني لو عندي two determinants وعايز اجمعهم مع بعض لازم يبقوا from the same dimension. This is number one. طيب number two, لازم they will have exactly similar rows or similar columns. The difference will be in one row or one column, and that's it. And this is completely different than matrices. Okay, for the determinant of a matrix with two identical rows, remember I told you about this, the value of the determinant will equal to 0, direct. Yeah, if I have any determinant with two rows exactly the same, or two columns exactly the same, the result will be 0. Also, for normalization, if you have the determinant, I'm sorry, for the identity matrix is equal to positive 1. It's a diagonal matrix. One of the remarks also, if you have a diagonal matrix, or an upper triangular matrix or lower triangular matrix, the value of the determinant will be very nice. Because all you have to do is to multiply the elements of the principal diagonal, and that's it. So what I mean is, if I have, for example, 5, 0, 0, and 6, okay, this determinant, which is a diagonal determinant, the value will be 30. That's it. If I have 1, 0, 0, 0, 2, 0, 0, 0, negative 1, the value of this determinant, you will accept no effort. The value will be negative 2. Okay? So if you have a diagonal matrix, the result or the value of the determinant will equal to the multiplication of its principal diagonal. Oh, by the idea. Any one of you can remember what's the trace of a matrix? Any one of you can remember what's the trace of a matrix? The trace of a matrix is the sum of the principal diagonal elements. Don't forget that. It just crossed my mind, so I wanted to just you to remember. Okay? Okay. These probabilities is telling you this in the slides. These probabilities seem strange, but reflect the fundamental probabilities of determinant. Note that determinant is a scalar, a real number. وانت شفت دلوقتي بيطلع مني. We will verify. بص الكومنت. This is very very good comment. And exactly I've told you this before we start. We will verify that the formulas to compute the determinants are not simple. They are not simple. And you've tried that. If I have a 5 by 5 or 4 by 4, it's really ridiculous. Are not simple, except for square matrices of orders 1, 2, and 3. The maximum 3, it's going to be really very simple. Once you start using Sarah's rule, it's going to be very simple. Okay. Theorem, let A be an M matrix. The determinant satisfies the following properties. If A has a 0 row, then the determinant of A will equal to 0. Stop. This rule or this point in this theorem reflects that Cramer method will be used only with the matrices that's with the same rank. So a unique solution only. Because if you have infinite number of solutions, one of the main rows, the rank is not going to equal to the columns. So you will have a 0 row embedded in it. This is why Cramer method is not going to work. Okay. Number 2, the value of the determinant changes. Oh, shouldn't do that. Changes sign if any 2 rows are interchanged. This is important. In matrices, you can get an equivalent matrix if you switch simply rows. But in determinants, if you switch rows, the value will be the same, but the sign will be an opposite. So if you go through row operations in determinants, you should be careful using switching rows. Because once you switch the rows, the sign of the value will change. معايا يا أحمد؟ دي معلومة مهمة جدا، خلي بالك. The value of the determinant changes sign if any 2 rows are interchanged. Thus, if a matrix B is obtained from matrix A by interchanging any 2 rows of A, then the determinant of B will equal to the negative, the determinant of A. That's if you have a matrix and you are going through row operations and you make a switch in this elementary matrix or so for rows, you should put in your mind or keep remembering this elementary process, because it will have a negative sign on the determinant relative to this operation. Also, the elementary row operation that adds to one row a multiple of another row, it will not change the value of the determinant. فاكر في الماتريسيز how many row operations do we have? 3 of them. The first is switching rows, so there is a difference between matrices and determinants. The second, or the major one that I'm usually using in order to develop series, which is multiplying a row by a number, then adding it on another row. In matrices, they are going to be the same. Also in determinants, they will be the same. Okay, the determinant of a diagonal matrix is the product of the diagonal entries, and we already saw that. Okay, same also goes for our triangular matrices. This property also really very nice. The determinant of a diagonal matrix is the product of the diagonal entries. For 5, I wrote it in just at the end of this slide, but it's really also very important. شباب خليكم معايا. Determinants of alpha times A. ايه اللي تفهمه من alpha times A؟ سيف، تفهم ايه من alpha times A؟ ال A ده stand for ايه؟ A symbol for a determinant or a symbol for a matrix? A matrix. طب لما الماتريكس بضربها في alpha, it means I've multiplied all the rows in this value, صح؟ So it will equal to alpha to the power of n times the determinant of A. حد واخد باله انا بقول ايه؟ طب ليه الديفرنس ده؟ طب ليه الديفرنس ده؟ لأن أنا لو بعمل multiplication أو بتيك common factor from a determinant, it will come out from one row. So if you multiply a matrix with 3 rows by 2, that means you will multiply the last row by 2, the second row by 2, the first row by 2. So actually, you multiply the value of the determinant by 2 to the power of 3 for the original one. This property is important. This one is important. Okay, and also signifies the differences between determinants and matrices. The proofs are really very simple for each and every one of these 5 properties of the matrices, the 0, the whatever. If, for example, if you want, if I want to prove the first one, I'm not going to go through plenty of proofs. Already I've sent you the slides, so you can go through them by yourself. You are capable of that. But I want just only to show you how simple it is to prove, for example, the first property. Like we want to prove that for any row, say row I, whatever row, any row that belongs to a determinant, general dimension, once it's equal to 0, the result will be 0. How to prove it? The proof is really very simple. It's really very simple. All I have to do, that's the determinant of the elements with the 0 number. I know that I can take a common from one row or from one common. So I will take the 0 as a common from Ri. So it will be a 0 times the value of the determinant. Whatever the value of the determinant is going to be, times 0, the result will be 0. Ahmed, فاهم انا بقول ايه؟ Proof, حلو البروف على فكرة it's really very nice here. مش فاهمه؟ تمام يعني؟ Okay. بيقول let's show how to use the definition. خلاص مش عايز اخش ده. A determinant 1 by 1 ده اللي انا قلت لك عليه هيساوي الفاليو على طول بتاعته. برضه البروف really very simple. يعني if I have a matrix 6 1 by 1, the value of the determinant will be 6. This is why take 6 out as a common, so it's going to be 6 times 1, so the result will be 6. So if I need a determinant for an A element, the value of the determinant will be A. Okay, also he is proving here to you how we got to evaluate a square determinant 2 by 2 by just multiplying the elements of the principal diagonal minus the elements of the secondary diagonals. The rule of this proof also is very, very simple. All I have to do is to how to manipulate the determinant relative to this matrix. So simply, if I have an A times B, بص كده نور وسلمى. بص كده يا نور، لو انا عندي ماتريكس A و B، دي معناها الدايمنشن بتاعها كام الاول؟ 1 2 صح كده؟ 1 2. بصي انا ممكن اكتبها ازاي؟ انا ممكن اكتبها A و 0 بلس 0 and B. انت معايا يا ملك؟ يعني بص اللعبه دي شباب، الحركه دي لذيذه قوي. بص كده لو انا عندي 2 و 6، this is a matrix 1 by 2. I can, if you like, we can write it like this. Yes or no? صح؟ اقدر ان انا to separate them. مش كده برضو؟ خلي بالك هو عمل ايه؟ قسم الماتريكس اللي هي A و B into how many matrices? 2 of them. بص الحركه دي يا نور برضه لذيذه قوي. انا اقدر اخد من دي A as a common، فيبقى ده 1 و 0 صح؟ لان انا اقدر اخد from the elements of any matrix a common factor. بالفعل انا عملت كده، انا بقيت A times 1 0. والتانيه بالظبط زيها بقت B times 0 1. This is the property that I will use in order to break this matrix into smaller and easier ones, and I will prove to you how to evaluate the value of this matrix. It's very, very simple. This is also for the second row. We can do the same. So if we have A, B, C, D, I can do it like A, 0, C, and D. And the other one will be 0, B, C, and D. Get the determinant of each one of them. Before, I can take A from this one, so I will have 1, 0, C, and D. This is going to be B, 0, 1, C, and D. I can repeat the same process, but with the second row. Okay, once more, I've repeated the same process with the second row. And remark that if I want to, for example, once you are doing this, you will have some determinants like that, which you have a whole column with zeros. And so this value will be 0. And also, this one will be 0. Remark for these two determinants, I have 1 and 0 and 0 and 1. I know the determinant value of a unit matrix, which is 1. Like, look at this matrix with this composition. If I want to replace the elements of these two rows, it will be a unit matrix. But the sign will be
Negative.
This is why you are getting the elements A times B minus C times D. This is this is from where it came. Okay? Last part. بصي تاني once more. انت شفت ازاي بعمل ده في rows, okay? How we do it with rows. The first row or the second. Then I will go for the main matrix. I will separate the first row. Exactly the same. Okay? So it's going to be A and 0, 0 and B. Now I can take A as a common from this matrix, and I can B as a common from this matrix. So we will end up having these two matrices. In a similar manner, I will do the same with this row and that row. I will make this 0 and D, then C and 0. Okay? So I am going to separate or to break this matrix into two of them. Can you see that? And in exactly in a similar manner for the last one, which is like this. Also, I will take C as a common, and I will take D as a common. I will take C as a common from here. I will take D as a common from here. This is the result of all of this. Once we do that, you will find some of these determinants with 0 columns, so the results will be zeros. They will disappear. You will end up having just only these two values. This one will equal to A times D times 1. But this one, if you switch the rows to be a unit matrix, in order to be able to, you know that the determinant of a unit matrix is equal to 1 for the previous properties. I will change the sign since I'm changing the rows of the determinant. So the value of this determinant is exactly the same. Those are the ones are remaining. I'm switching the rows, so the result will be negative. This determinant value is 1, and that determinant value is, so it's going to be A times D minus B times C, which is from the beginning, we already did go through this. For evaluating a determinant with a 2 rows, 2 columns, all I have to do, multiply the elements of the principal diagonal minus the elements of the secondary diagonal. This is the proof how you get the main formula for expanding a 2 by 2. And it can be generalized. Okay.
دكتور
ها؟
ينفع use previous proof common factor property؟
كل حاجة. Okay. And they actually are written with you in the slides. But I thought I shouldn't go, just I thought through you, I did go through it with the 2 of the properties, which are really very simple, and it can be applied for all of them. I didn't want to go through all of this in order not to waste your time and to feel good. Okay. Okay, this is the bottom line. Note that in the exchange of 2 rows, it changes the sign of the determinant. I want you to keep this in mind in all times. Here, determinant of an A3 by 3. This is the Saras rule that I explained to you, okay, before we start. If I want to evaluate the determinant value for this matrix, I will multiply simply the elements of the principal diagonal. Then I will go for A21 times A32 times A13, okay, and so on. It's exactly written in front of you, and this is called Saras rule. Note that these 6 terms has exactly 1 element of each row and 1 element of each column. على فكرة احنا ممكن نعملها بكده بحيث انك انت تاخد الفيرست 2 رو columns وتنقلهم بعدين تمشي diagonally 3 بعدين ماينس 3. مالكش دعوة باللي تحت، انت كفاية عليك سلس اللي فوق. اوكي؟ بقى. Exercise. Compute the determinants. Exercise ده لذيذة. الناس اللي قاعدة معايا من البداية مستر بلال تاني متحضر المحاضرة كلها دلوقتي. تعالى بقى قول لي أول determinant اللي هو 1 2 3 and 4 أحسبه إزاي؟
تعمل 1 times 4 2 times 3.
يبقى 1 times 4 which is 4 minus 6 so the result will be negative 2. keep it in mind. خليه معاك. طيب بص على ده وبص على اللي جنبه نور وسلمى. كفاية. بجد كفايه. بص على نمبر بي معايا بلال، تفتكر الديفرنس هيبقى ازاي؟
الديفرنس في ايه؟
ها
البوتtom رو.
ها عملت ايه في البوتوم رو؟
كل حاجه
ده اهو ده اهو. بص على الفيرست، هو الفيرست. سكند رو عملت فيه ايه؟
عملنا بلس اللي فوق اللي تحت.
اوكي؟ عملت adding times 1 وadded على السكند رو، صح كده؟ يبقى اذا تفتكر that the value of this determinant will be different than the first one?
No.
ها لا. ليه؟ لأن البروبرتيز بتاعت الديترمينانت if you multiplied a row and adding this row into another row, the result will be the same. سبحان الله. فعلا 1 times 4 is going to be 4 minus 6, so the result will be negative 2. Exactly in a similar manner, 1 times 6 it's going to be 6 minus 8, so it's going to be negative 2. He's trying the probability in front of you. طيب اسمك ايه؟ يوسف. معايا؟ طيب بص على دي وبص على دي، تفتكر الديفرنس هي في ايه؟
في اللي فوق
عملت ايه؟
خليتها باي.
يعني انت عملت multiplication ل 1 row باي فاليو. طيب تعالى نحسب، احنا حسبنا ده بنيجاتيف 2، خلي الفاليو دي معاك. تعالى احسب ده تاني once more. هتدي لك ها؟
باي تايمز 4
minus 6, so it's going to be negative 2 pi. So actually, if I multiply a row by a certain value, it's going to equal to the determinant by this value. طيب تعال بص على دي 1 2 3 4. ايه الفرق بين ده وبين البروبابيلتي بين سي؟ فرق بين اف وبين سي. عملت تايمز باي in both two rows. اوكي؟ لذلك لما تيجي تحسب ده هيدي لك نيجاتيف 2 باي سكوير. لانك كده اكشوال عملت مالتيبليكيشن في كام رو؟ في التو روز، وبالتالي ده define البروبابيلتي ان لو خدت common from the whole matrix it will be to the power of the rows. اوكي؟ برضو الاخيره انا هنا عملت ايه؟ حد يقول لي هنا عملت ايه؟ خدت الفيرست رو ملتبلايد صح كده؟ الفيرست رو ملتبلايد ان نيجاتيف باي وادد على السكند رو. ها سيف without calculations. تقدر تقول لي الفاليو بتاعت الديترمنت ده ممكن يبقى بكام؟ نفسه معايا هيبقى بنيجاتيف 2. ليه اشمعنى بنيجاتيف 2؟
عشان
لان بكل بساطه انا ملتبلايد one of the row with a certain value وادد على الاذر رو. معايا نور؟ ها once more
What I'm saying
ده
is
يبقى 4 minus 2 باي بعدين minus 6 وبلس 2 باي فالبوزيتيف 2 باي والكانسل ده نيجاتيف 2 باي وهيبقى عندك ال 4 بالبوزيتيف والنيجاتيف 6 so the result will be negative 2 exactly like the previous one. معايا جميل؟ تاني once more look at this one this is the name صح؟
yes.
ايه الديفرنس between number A و number E؟ I've multiplied the first row in negative pi. Then I've added it on the last row. Supposed to be the same results. So 1 times 4, 4. Minus 6, so it's negative 2. Keep it. Okay, let's go for the bigger one. 1 times 4 minus 2 pi, it's going to be 4 minus 2 over pi. Then minus 2 times the 3 minus pi. So negative 2 times 3 is going to be negative 6. 4 positive minus 6 is going to be negative 2. Keep it. Then you will have negative 2 pi minus the negative of 2 times negative pi, which is going to be positive 2 pi. So they will cancel each other. So the result will be negative 2. So instead of just mentioning the steps, you already tested on an example, which is I can see it's very simple. طبعا of course الريزلتس موجوده عندك تحت اهي وهي الاجابات بتاعتك بالظبط زي ما احنا